I think it's working. Is it working? Yeah. All right, let's give it one more minute for everybody to settle down. Take your time. 5 minutes is okay, more. Right. Welcome, everybody, the 2023 Dr. Carl Zorowski Distinguished Lecture Series. This was established a little more than 3 years back by Professor Zorowski, who many of you might not know was a department head and also an associate dean in the college. Is major contributions to our program. Many of you, and especially the students who are in the senior design, Dr. Zorowski designed the mechanical engineering senior design, especially funded by industry. So a lot of credit for that goes to him. I wanted to say a few things before we get to other things. We'll have Hank Cook will be talking a little bit about Dr. Zorowski's contributions. He was class of 76 in a minute, just a minute, Hank. I just want to thank a few people for making this happen. Of course, Professor Zorowski himself, I met him just before the pandemic. He was very excited about creating a series, lecture series, and he was very passionate about automotive racing, so it's a pertinent topic today. Second thing, I want to thank Mrs. Zorowski. Louis is right here, somewhere in the middle, right there. And thank you for your help, and of course, Dr. Zorowski's 3 children. They were also very excited about having something like this happen. In addition, there are other people who helped make this event happen. Jessica, my assistant, executive assistant. Jack Borden is right here, helping us out with all the setting up, the PR, the great pamphlet you have, all that stuff, and getting the word out on social media. So Jack was contributing to that. And one of our student workers, Eric, was very helpful in setting up the reception and also this. So I want to thank them and for doing a great job on this, setting up this event and having everybody come here. So at this point, I want to introduce Hank Cook, class of 76, to talk about Professor Zorowski.
Well, thank you, Dr. Akkad, and good morning, everyone. I'm Hank Cook, and I'm looking forward to today's presentation. But before our speakers introduced, I'd like to add to Dr. Akkad's remarks. As he said, I'm a 1976 graduate, and I count myself very fortunate that for my entire time at NC State, Carl Zorowski was the Mechanical and Aerospace Engineering Department head. In and amongst Dr. Z's many accomplishments, one of the most significant was the relationship that he developed with his students. And I know I benefited from that. The students who are part of the IMSA Institute have benefited from that. Carl co-founded the IMSA Institute. The students that he took to China certainly benefited from that. And all you students here are benefiting from that in this lecture that, as Dr. Akkad said, Carl endowed himself. I think I'm correct that Dr. Zorowski retired in 1997, but what I'm sure about is that he didn't fully retire for another almost 20 years. I'm so pleased today that 4 of my 1976 classmates could join me here. All of us knew Dr. Zorowski very well and share in my gratitude for how he enriched our time as students. And so I'd like to recognize them. Courtney Johnson, just raise your hand, Courtney. Mike Malpas, Hayden Moore, and Jim Baird. A 5th classmate, Ed Ridgeberg, caught a cold and sent me his regrets yesterday. Didn't want to pass anything along to us. But now, again, as Dr. Akkad mentioned, Carl was a motorsports enthusiast, and so this topic is really great. I know he would be especially pleased with it, so I'm going to turn it back over to you to introduce the speaker.
Thank you, Hank. Again, there's a brick also in front of EB3 with Professor Zorowski's name dedicated by the class of 76. So it's really wonderful to see his name, and we would love to see Dr. Zorowski's names on many things in the department, because his imprint on the department has been long and justifiably should be continued forever. So without further ado, I'm here to introduce our speaker today, our third speaker in the Zorowski lecture series, Dr. Eric S. Warren. It was great because he's also got all his 3 degrees at NC State, got his BS in 91, MS in 93, and PhD in 97 in aerospace engineering, and he's spent last 25 years working in motorsports. He actually was part of a big Langley funded program at NC State in the 90s, and that's where he got his degrees for working on topics in aerodynamics. In 2020, after an 8-year tenure at Richard Childress Racing as Vice President and Chief Technology Officer, Dr. Warren joined General Motors as the Director of Motorsports Competition NASCAR programs, and Dr. Warren also is a board member of the Institute of Digital Engineering USA. At General Motors, in addition to managing NASCAR program, Dr. Warren has led the development of GM Motorsports organization and the construction of the new GM Charlotte Technical Center in Concord, North Carolina, which I had an opportunity to visit a few months back. A fantastic facility. I think Eric is really enjoying leading such a diverse facility there. Active research interests include optimal control methods for optimization of vehicle performance, DIL, XIL simulation, tire modeling, aerodynamics, real-time data analytics, race strategy optimization, and digital engineering architecture. More importantly, Eric recently was promoted to an even higher position involving entire GM racing across the board. So he'll share some of that with us. But without further ado, Eric, please give a round of applause.
Good morning, everyone. Thanks for joining. As everyone said, I spent a lot of time here at NC State, 10 years. My son went here, actually, so I bleed red. And I tell everyone I'd probably still be in grad school, but worked with Basil, Dr. Hassan. If my wife hadn't gotten pregnant with my son, I'd probably still be here. So my heart's definitely here, and I love coming back, and hopefully give everyone a little bit of insight of motorsports. Everyone asks, how did I get into racing, and did I grow up short track racing? And I never saw a race until I finished my PhD and got a job in racing. I happened to meet one of the team owners, Michael Cranifus, on a visit. He convinced me to get into racing, and my first day on the job was at Indianapolis Motor Speedway. So just a testament really to what a great NC State education can give you. The path really leading race teams, and everything I learned here, really, it's amazing. And the application, everybody talked about NASCAR at the time, and I did recently take over all of GM Motorsports, but this was a little heavy NASCAR, but at the same time, it's the same all across the sports. But really, your education, what you think you're doing, I was doing boundary layer transition and hypersonics, and ended up in racing, but it's amazing the technology and what you learn, how it can be applied, and really, it's learning how to learn, and racing is a great example of that. So really, the topic of it is really to talk about when we race, what we're really doing today is actually digitally racing. And what I mean by that is we're doing simulation, everything behind the scenes. We have to show up at the racetrack and win on the first lap. So all the things that happen behind the scenes, what we call digital engineering, this drive to virtual racing, really is where the war is today. And I'll try to touch on a little bit all the technologies, and hopefully inspire some people to learn more. This picture is when we won the Daytona 500 this year. So now that I'm taking over all the racing, I plan on winning the Indy 500, the 24-hour Le Mans, and the Daytona 500 the first year, so we're going to try it. Now here's a little bit of teaser video to get everybody just a good overview of GM racing.
with your push. Run hard.
Welcome to Daytona International Speedway for the Rolex 24.
And the 24-hour starts right now. The Chevy Corvette leading the class.
Speaking of GM machinery, how about the Cadillac racing machine up front in the lead?
All right, so just talking about a little bit of last year's success GM had and give you an idea of how broad and how many different race series we race in. Starting this year on the NASCAR side, we've won 4 out of the first 5 races. First time it's happened since 2001. So the program's gotten really strong as far as our performance on the racetrack, and I'll try to give you, again, the insight of what all goes on behind that and what we're still actually driving and working on. So as shown in the video, here are kind of the major series we are racing in NASCAR. There's 3 different series, if you're not familiar with it. The top level is called the Cup Series, then the second is Xfinity, and then there's a Truck Series. IndyCar racing, and then IMSA and what's called World Endurance Championship. New vehicle this year, it's a brand new Cadillac. It's a hybrid, it's called LMDH. The first race was 24 hours at Daytona, and then they just raced at Sebring. So that car races in 2 different series. IMSA is mostly in the US, and the WEC is actually all over the world. Then one of the other exciting things that GM is currently doing that I'm leading is we've applied for entry to get into Formula One. So we're partnering with Cadillac brand with Andretti. Knock on wood, our chances look good, but it's, as all racing is, heavy political. But we're in the process of this, should find out in June, which will be a huge step. General Motors has never been involved in Formula One. And the entire company, the board of directors, everybody's motivated, so it's going to be exciting to see that play out. This is just an eye chart, but give you a good example. It's a calendar of all the different series that we race across the bottom here. You know, and you look at a typical weekend, you know, each month going across. And so the challenge for us really is you pick one of these weeks, say right here, middle of July, there's 8 races going on worldwide at the same time. And so as our whole organization, if we look at the size of it and all of what we're trying to analyze and evaluate, there's a lot going on. So really we have a lot of race teams that are customers, and I want to kind of describe what our role is in racing and how in some series we own the whole car, but most of the series we're partners with the race teams. And so if you look at all these race teams, there are a lot of famous names that we've been involved with historically. And really, why do we race? You know, it's really to deliver those services to the race teams and make them successful. But in reality, we're also there to sell cars. So it's really about building brand identity and connecting with the customer. And so each race series is a little different. A lot of times NASCAR has been founded on, hey, I can go buy that car in the showroom, which is not true. They're really not stock cars. Hadn't been for a long time. But it's really the people in the stands, they start to understand that General Motors and Chevy, the technology involved in it, really builds that affinity. So when they're going to buy cars, they have that brand awareness, whether it's Chevy and NASCAR and the US racing or Cadillac that we're trying to bring. But it's also becoming much more of a technology transfer. Originally in, say, Corvette, there are actually parts and engines that really, go across racing. But technology transfer now is much more about the digital engineering. GM as a whole is changing their process from building a lot of prototypes, a lot of proving grounds, really historically understanding what it takes to build a car. It takes a lot of different prototype vehicles, hundreds and even thousands of them. So now the drive really is to do it all virtually, where the first car is, sellable. Much like aerospace or defense, the first airplane has to fly. The whole idea is to really bring virtual engineering and the digital engineering process into the company. One, it helps develop the cars faster, so new models, new shapes can come out quicker, but also it's a lot more cost effective with all of that hardware. Training engineers, people is really also a key part of it. And racing really allows you to develop a lot of new technologies, particularly around data analytics and race engineering, digital engineering. We'll talk about it. The primary reason is because we race every week. So as we're trying to correlate data, simulate data, much as many of you have to sit in a test and come up with answers and get graded, we get graded every week. And if you think about a lot of car development programs or military programs, it's years or months before you actually understand whether your product worked. For us in racing, it's every week. And so time really is a big factor, and we'll talk a lot about that. So if we look at who we are, GM Motorsports has been growing. 3 years ago when I came from one of the race teams, GM Motorsports had 3 employees, maybe 5 employees that were all basically marketing. So they funded all of the racing with third-party engineering groups. So the board and the president and CEO, Mary Barra, and President Mark Royce, wanted to really bring it in-house. Again, connect to GM Engineering. So we started building up GM Motorsports. We have about 200 people. We've built a new Charlotte Technical Center in Concord. If anyone has not seen it, it's a great facility and tour. And also the GM Milford Proving Grounds. There's a building there that really is focused on motorsports. And then IT, there's a lot of different innovation centers for General Motors across the country. There's one in Austin that a lot of our specialized IT personnel work out of. And then also, you know, if you look at the combination between the different GM engineering groups, in our tire modeling group, for example, we have about 25 engineers that basically are working solely on modeling tires across all the series, and we'll get into that a little bit as well. So the Charlotte Technical Center, gotta admit, I say a lot, ever since I got out of school, I can't tell you how many times I've said they don't teach you that in engineering school. There's a lot of people things, leadership things that you have to learn. Building a commercial building for a big corporation was definitely not something I learned in engineering school. So we completed that this past October. It's about 150,000 square feet. Has 3 full driver-in-the-loop simulators you'll be able to see some pictures of. A lot of very unique equipment, scanning equipment, KNC or Kinemax compliant suspension rigs. A lot of, there's a command center with a lot of data analytics and stuff we do with the team, but it's really a building set up to characterize a vehicle so that you can build vehicle models. Wind shear, full-scale Aerodynamics wind tunnel is right across the airport from there. So in a 1 mile radius, you can completely characterize the vehicle, digitize and build the model. So it's really centered on pushing digital engineering and that virtual work. Here's some other pictures of the front of the building. Here's a picture of the simulator in the bottom left. It's Anthony Best Dynamics, full, you know, really high resolution, high response time. Here's a Kinemax KNC rig in the middle. A lot of different work bays, and there's a little bit of one of the command centers up there on the upper right. So really kind of, it's amazing this diagram, the life that it's had. My second day on the job, I got pushed into a meeting to come up with a plan. I put this together that's stood the test of time, and it's really an idea of what GM Motorsports is. So the GM Production Engineering at the top, you know, I report now to the Director of Global Product Development, Doug Parks at GM. He has about 26,000 engineers. There are about 5,000 engineers in what's called Virtual Design Development, VDDV, doing nothing but simulation of all types of things, crashes, vehicle dynamics, aerodynamics. So really, you know, when we were sponsoring a third party to run racing, there really was not that connection to GM Production Engineering. So GM Motorsports, the intent is basically to go between the race teams and actually connect the racetrack to GM Production Engineering. And there's a lot of, as we talk through that, a lot of that is the processes and techniques that it takes to do it quickly in racing. Changes the way you have to think and the way you have to structure all the digital engineering process, because you can't take 2 months to run a simulation in racing. You have to do it weekly, so you have to make different choices and different processes. So we took all these race teams used to have their own aerodynamics program, CFD program, simulation. We took all that off of the teams. Myself came from one of the teams and built GM Motorsports to kind of create all these common tools that now all the teams use together. So in NASCAR, when you see all the Chevy teams, we're sharing setups across the teams, the information. There's a lot of collaboration, all of it common tools that we've built. So if you talk about racing and really what it boils down to, what's successful in winning a race are really these 6 things. And fundamentally, that's all it really is. I've gotten to a lot of arguments over the years to show that this really is all that matters. And it's the driver, which comes down to the actual talent of the driver, but it's also what information does he have, what does he understand about how cars interact against each other, feedback, training of him, mental training, heat training, anything related to driver performance is of course a key factor. Engine is really kind of longitudinal acceleration capability, so it's driving, braking, all those types. The aero, there's only two things that affect the performance of the car. Increase the envelope of performance, it's the engine and the aerodynamics. You know, it actually increases the potential of the car, but then it's actually the tire and the tire force optimization that actually gets that potential out. So setups, chassis, all those types of things really is how the loads are distributed and how the vehicle dynamics, you know, puts load into the tires, which creates the lateral forces, and optimizing that and managing that is really that key fundamental. Of course, then in the event execution, race event execution, and the pit stop. So really you can win a race by showing up with a great engine at a track or making a great pit call, but you can't win championships unless really you are the best at each one of those. And so over the last 3 years, we've dominated many of the series, you know, and really the focus is constantly building up our expertise in these areas. So I'm going to just try to talk a little bit. Again, given the time, it's going to be difficult to hit much detail, but you know, our common tool set, really where we support the race teams, is in the aerodynamic development. We do all the CFD work, all the full-scale wind tunnel work. Used to do a lot of scale model work. We're doing much more CFD and validating full scale than we are scale model work. Tire modeling is a huge thing we'll touch on a little bit. You know, getting into really understanding the thermal characteristics, the asphalt. It's amazing how the disparities of the asphalt and the types of rocks and the micro roughness, how super critical it is to how the tire works. And as you understand more about it and managing the temperature of the tire, you have to really bring that into simulation as you start doing correlation with driver in a loop. If you don't have those thermal characteristics in the tire, the driver just gets out and says it's not even close. And so it really is a critical thing. The AI machine learning is so critical in what we do, particularly race strategy, where we'll have a little video on that. But you know, it's really this digital engineering approach. How do you tie all the tools together? How do you tie the information together? How do all the engineers know what's the car that the Hendrick Motorsports 9 team is going to unload at COTA this weekend? And how do you simulate that? You have to know what all the parts are that are on that car, and it takes a lot. Talking about vehicle simulation, at different points in time, I know the department here has touched on a little bit of Daimola multi-body modeling, but our models are all multi-body models that are based on Modelica, which is like an open source multi-body modeling. So we have offline simulation that the race engineers run at the racetrack. They can walk right into the driver and loop facility, set their laptop down, hit a button, run on the simulator. The tracks are scanned down to less than 2 millimeter accuracy. So if you think about a racetrack and all the bumps and all the cracks and things that are going on, we have them simulated less than 2 millimeter accuracy to get all the content, all of the bumps, everything is running on that racetrack digitally. Aerodynamics, CFD, you know, it's been around a long time. I joke, I tell everybody in racing, you know, I knew what CFD was before people could spell it. But, you know, and, you know, so much of the work is done there. So we create a lot of tools. You know, we run about anywhere from 30 to 100 CFD runs a night that are about 500 million grid point cases, pretty large cases just for NASCAR. So if you look at it, there's thousands of runs done, full 3D, and a lot of different techniques to really understand, you know, the car from a development standpoint, but also how it behaves in traffic next to the wall, a lot of different factors. But we're also creating a lot of software so that we can look at the images and do a lot of the comparisons. So we're as much a software creation company as we are engineering. Here's one example. As we were developing, say, our 2023 car, we do a lot of adjoint methods. Much of what we do, because the way tech works in the tech inspections, is they give you tolerance. So if you get 100,000ths of an inch tolerance, we're going to play in that. We're going to maximize every single piece of that. And so we do a lot of adjoint methods to just look at surface sensitivities globally, and really it drives a lot of our aero development. It's a good example of tying that CFD and aero development into the full-scale wind tunnel. The whole front of the car is all rapid prototype parts. It's, you know, there's a frame behind that. So as we develop CFD, we can validate straight in the wind tunnel with a full-size car. Main reason we did on this is the actual submission from the sanctioning body required the full-scale car be tested. So we want to make sure we understood exactly every single thing. So that process happens very rapidly. The whole front shell of that car can basically be built in less than a day. The GM RP lab has about 1,000 3D printers, and so we can turn around things quickly. Now getting in front of the production side is another thing, but once we do, they can move really quick. So some other things on aero that come into play is, the aero map, the aero data has to be put into kind of a aero map or fitting form so the simulation can use it. So there's also a lot of plotting packages so the teams can kind of understand where do they need to run the race car. So there's a lot of that. But as you get into the other interactions in the system, the aerodynamics plays a really key role in the tire modeling again, because you're trying to look at the thermal modeling of the tire. So of course the convection to the air, the brakes. So modeling the brakes fully from the heat transfers, the conjugate heat transfer through the parts, as well as the aero side of it. It's really important to get that heat input to predict the tire temperature correctly. So aerodynamics plays a lot bigger role than just external aero or even internal aero in the combustion side. All these systems have an aero component. This is a complex tire chart for a reason. This is tire modeling 101 in racing and NASCAR. So you kind of start out on the left. You have these tire test rigs. There's one that basically the industry uses up in Virginia Tech. It's called SOVA G-caps. So the thing about these tire rigs is they run on sandpaper. And so if you think about the spectral and the sandpaper, how it compares to asphalt, in reality it's not even close. Over years people would go on these tire rigs, they would fit basically that data, fit a what's called a Pajeca magic formula, which is just a curve fit, and they would go run. Well, over time we realized from testing on the racetrack, we test with these wheel force transducers. Each one of these sensors are about 120,000. They measure all 3 forces, 3 moments on the car. So the OEM test every time there's a new tire. We're testing on the racetrack to gather real data on the asphalt. So then we're trying to kind of merge those two. What do we see from the racetrack? Driver correlation at the DIL from this test, and then we end up scaling this data to take into account what we see the actual mu and the friction characteristics of the track. That's kind of been historically what happens, and you can see all these iteration loops and things. It's to get it right is virtually impossible, because there's a lot of the physics that's actually missing from the model, which is the key part. You can spend a lot of time fitting and data, but if you're missing some of the core elements, you're basically just creating an issue. So then how do you get more advanced? You got to start looking at the thermal characterization of the tire, the actual makeup of the tire, how heat flows through the contact patch. You're looking at how the contact patch and the pressure distribution is on the ground for different loads, cambers, different things. And then the rubber characteristics itself. The tire companies won't let you actually take the tire, cut it up, and do typical testing. So the racing industry has kind of developed this really novel way to non-destructively get the rubber characteristics. It's kind of the loss modulus and the storage modulus to really understand the rubber. And then you're getting into wear modeling. How does the surface of the tire, the ablation, and how the wear of the tire, and how does it affect it with different surface references. So there's a tremendous amount of effort going on here. And this is any racing program worldwide. So if you look at the racetrack, these are 2 different tracks. One is Richmond, one is Phoenix, where we run the same tire. And if you this is kind of a proliphometer measurement of the asphalt. We're kind of zoomed in. If you look at the 2 tracks, you run the same tire on both tracks. Phoenix has a lot different, not near the macro roughness that Richmond does. And what the tire wants is completely different for each one of these 2 racetracks. If this tire wants really low pressure, this tire actually wants higher pressure. So until you really start to understand that, all of your simulation, all of the digital engineering tools you have are dependent on that tire and road interface. And so you can't ever really ignore and trying to make that better. So then if you look at what the challenges are in racing, particularly NASCAR, we're typically dealing with less than 0.5% performance from 10th place to first place. So if you're trying to simulate the lap and try to find that performance of all the different variables, you're looking at really, really small differences. And so it becomes much more difficult to simulate the whole system. And so you're constantly challenging all of the inputs and learning in a iterative manner. You know, we have to show up with no practice most of the time now. There's very little practice. And at all types of different racetracks. In NASCAR, there's different banking, road courses, ovals. There's a lot of different variables that are thrown. And the biggest thing is the human side of it. You're racing 38 out of 40 weeks. So you're coming after one race, getting home Sunday night, Monday morning, you're trying to debrief, you're trying to correlate all the simulation, what happened and didn't work, this worked, that didn't work. And then you're right back at the racetrack, leaving going Thursday to Friday. So how you actually understand your competitors, all the systems, that's where a lot of the data analytics, and try to present it something quickly so you can react. Here's another, start talking about a little bit more deep into the data and the tools, and try to give you a little flavor of what goes on there.
In motorsports, data and the velocity with which we can analyze and apply learnings have a direct correlation to helping our race teams reach the podium each weekend. In a NASCAR race, telemetry sensors in-car record and measure speed, throttle, braking, and steering. Advanced GPS monitors the position of cars on the track. From GM's Charlotte Technical Center, our in-race strategy tool, Pit Row, ingests and analyzes over 100,000 points of telemetry data every lap, including lap times, track conditions, pit stops, and more. Harnessing the power of machine learning, our cloud-based application performs more than 1 million calculations per lap and recommends optimum race strategy on every lap for any car in the field. Many key strategy decisions like track position, chassis adjustments, and when to pit for tires or fuel were historically made instinctively by drivers and crew chiefs and engineers based off of their experience and intuition. Pit Row is given the rules of the game and plays them over and over until it learns all the possibilities and potential outcomes, developing a winning strategy for every situation. During a live race, our machine learning models dynamically update the recommendations. The Pit Row interface displays the best choice of 4 suggestions for every pit stop. Stay out on the track, pit for fuel, for 2 tires, or 4 tires. And in post-race, we debrief with the team and leverage Pit Row to replay, review, and analyze previous races while creating any combination of race scenarios in its simulation tool to evaluate our performance and tweak our models. In the near future, we will expand Pit Row to all of GM Motorsports as we move to dominate every series.
So really when we talk about digital engineering, it's really about combining the design, the simulation, and then the actual data. And how do I use data to integrate those tools and also to make those tools better. So we'll touch on that just briefly. If we look at a typical NASCAR race, and this is true any race series, and particularly Formula One, there's a tremendous amount of data coming off the vehicles. But you have data from different data sources. You have data from the people on pit road. If you look in the middle of the racetrack over there, you got crew chiefs that are talking back and forth, so there's verbal communication. You know, a lot of the radio traffic between the crew chiefs and the drivers is public. So we have live algorithms going, doing voice to text to analyze that data. So if a driver says some comment, it's all kind of analyzed. So we know whether it's our driver that has that issue or whether the whole field has that issue. Then there's telemetry coming off the car, like you said, GPS. So you know every moment what spot on the racetrack that car is. You've got basic, the path that it takes, so you can calculate a lot, but you get lateral acceleration, different things to kind of quantify where the friction in the track is. And all that stuff has to get up to basically somewhere in the cloud where we can do different, like we said, the race strategy, pit row analysis on it. And then now you're pushing it back to the race teams, and they're all trying to collaborate. So there's a lot of data moving, a lot of systems that have to get built to be able to use this live during a race. This gives you a general idea of all the, from an IT technology standpoint, kind of all the whole, what we call the taxonomy and what we're trying to build. So if we look at the 3 race series at the top, you know, there's different analysis and analytics There's what we call vehicle gateway, which is really the database that really identifies what is the car at that moment. So we can go back 3 years ago and say, I want to run the third lap on, say, the 24 car at this racetrack. All the information that's necessary to reproduce that in simulation, whether it's the ambient conditions, with infrared track conditions, the data of the car itself, all the aero data, that's all built in this gateway. And then the telemetry coming off the car, how you analyze it, how you view it, how do you take action on it, and then of course the vehicle simulation, which is really, you know, the word digital twin gets overused, but that's really what it is. You're trying to simulate the car, and then as you can do that more real time, a lot of the parameters that I didn't know, I now can look at what must be true type analysis to actually identify through machine learning some of these unknown parameters. A lot going on, a lot of things have to talk to each other. So when you talk about digital engineering, it's really all of these systems. How do they get built together and then used? Talk quickly about the Pit Row Analytics race strategy tools. So we've been doing this about 9 years. It was actually done at RCR. So it really started with the real-time information coming from the racetrack, and we really started looking at how do we use machine learning to really identify information about the performance of the car. So, and we'll talk about a little bit the different factors. And then during the race, you got to be able to use it. So at first, when we started, we were plotting graphs to show, okay, here's the effect of pitting now or taking 4 tires, and it really, the crew chiefs are the people that were making decisions on the track. 3 people could look at the graph and they'd come up with 3 conclusions. So basically, at one point, said, okay, that's where the green light box is. We said, okay, we're going to make the decision. There's no disputing. It says pit of 4 tires at this lap. And so that way on Monday, we would tell the people, we're not going to force you to follow the tool, but if you don't follow it and it doesn't go well, we're going to talk about it. So, you know, it's kind of like a quarterback coming off an NFL football field. You know, Tom Brady throws an interception. The first thing he does is goes and he looks at the video, talks with someone about what happened. That's a lot about what this system does. It makes predictions, but it, you know, and it only gets better by that feedback. And so constantly evolving on technology, because the faster you can analyze it, the more you can be accurate. So really what it does, it starts on the left and takes the data sources, and this is constantly increasing in time. You have telemetry off the car, the vehicle. You have timing and scoring, like different sections of the track, what order you're in, how far you are from competitors. You got pit data, so you understand about the pit crews, and so over time, you can evaluate how good a driver is coming down pit road, how good the pit stop is. You kind of create all these characteristics of drivers and teams. And then then you have to basically clean that data, manage it, process it with the models, and then do something with it. So if we talk about what goes on behind the scenes, there are a lot of factors that affect the recommendation. It's what we call adjusted lap time, which is, if I think about a race car, its performance is a function of distance to another car, how many laps are on tires, weather, all these different factors. Did he have 2 tires or 4 tires? What fuels he got in it? So we try to take all those out to kind of really compute what is the fundamental performance of that car. Then I can place it in different scenarios, war games let's call it. I can look at it against competitors, and that way I can play out if I took 2 tires and I gained 6 seconds on a pit stop, what's that going to net out 10 laps from now or after a pit stop? And then there's all these competitor strategy and caution probabilities. So what happens is this tool creates an optimum strategy, not just for your car, for every car in the field, and it's both under green flag running and then also if a caution happened. But over time, we also now compute, not only do we know what the optimum strategy is, we have a prediction of what the competitors are going to do based on their history. Because at certain times, in these certain situations, people are making decisions, drivers are overriding decisions. You kind of know the more likelihood of what a particular team is going to do. So all those factors come into saying, okay, this is the optimum strategy. And then telemetry, same thing. Information coming off the car, you know where you're losing time to a competitor. You have to bring all that together, put that in a tool that actually gets, you know, delivered to not only the strategy tool but also the teams. Because if I'm going to pit in a certain sequence and I know I'm going to come out and I'm going to pass this car at their weakness, if they're weak getting into turn 1 or whatever, then that's going to change the decision to the good or to the bad, depending upon where they pass the other car. So a lot of passing going on. So how does this all how do we analyze where we're at? You know, the challenge that we always have, it is the default nature of engineers particularly to just work on kind of this maturity curve of trying to figure out what happened and why it happened. You know, there's very few that want to step out and be predictive, right? They don't want to predict before the teams go to the racetrack what the lap time is going to be. But in reality, until you can be predictive and be accurate at being predictive, you can't really optimize, right? If you think about it, you can spend all this time trying to optimize down here, but if you can't predict the performance, you're just burning electrons. And this happens all the time, right? You have to really understand and have confidence that what you're actually simulating is reality. And then you can actually then optimize. And then as you get into the more advanced machine learning things, you actually can learn things on the car that you had no way to even identify that pattern was there. So really our goal is to really move up this curve. We have to be predictive, right? And then one thing that's very important, and this is the thing that racing really helps in GM, is the race starts on Sunday whether you're there or not. So just like a test, the test is going to start. If you're not there, you miss out, right? And so there's no, hey, I need another week, I need another month. You have to make a decision. So at that point in time, you always say you never get done. You always run out of time. So time is that factor which really changes the main variable of what you're actually trying to do. Again, so not only is it important to be able to tie all these tools together using data, being able to be more predictive, but now I have to learn and have to do it quickly. So there's a large part of digital engineering that really is how do you extract the lessons learned, how do I have confidence in it, how do I move forward faster. So then as we get into, this is just a thing I pulled out of a couple papers that, you know, how do you speed things up, right? The technology of building elaborate simulations. CFD's gotten much more complicated. Vehicle dynamics, we're able to simulate more things. But now when I have to step in a driver and loop simulator, I have to do it real time. That model has to run real time. So I can have a complex tire model that does a great job of predicting tire performance, but if it can't run real time, I can't do anything with it. So you end up with a lot of these different types of models that you see this intersection of, say, a high fidelity CFD simulation, or you have just a bunch of measured data that there's a lot of big data. You hear machine learning just churning on the data that gives you something. And you kind of have these intersections of both. So if you think about, you know, we get into what's called a lot of surrogate modeling, like trying to take the physical simulation, can I build a machine learning model to reproduce that simulation much faster? And so this is kind of just a schematic. You can think of it in a simple sense. From the aero data, you're gathering an air map and a wind tunnel, and you look at the ride heights and all those things, and you're just fitting a polynomial to it, right? So instead of obviously running the car in the wind tunnel every time you need to do something, you create just a fit to it. So a lot of times a surrogate model is just a polynomial or a fit, and then I use that fit in my methods and how you go about creating that. Well, you can also do that with much more complex simulations where it's an engine model, a vehicle dynamics model, a tire model, get into other methods, a lot of neural network stuff with tire modeling to kind of create, and you know, you're really looking for is the input and the output going to match? And so that you basically take that simulation, create a digital surrogate, and that's what you're actually using at different times and depending upon the speed and the requirements. And then lastly, I kind of stole this out of the Department of Defense digital engineering strategy to talk about what are all the components. And surprisingly, you know, this the last one, the transforming the culture in the workforce is the biggest challenge. But you know, you have to actually start when you're modeling something. Say you're designing a part in CAD. You know, you have to understand how that part's going to be used down the line in a simulation. So all the data that needs to come with it, this model-based systems engineering really has to start from the foundation. You know, in this authoritative sense of truth, there's a lot of, is really understanding who decides what the part is and how do you know that you have the right part. and the right system. And if I want to look at lap 9 of a previous race, how do I know that I have the actual piece? It's really critical. You know, there's one story that I tell a lot. I learned in GM. We were sitting in a meeting on tire modeling, and what used to happen is GM would work with all the tire manufacturers and say, hey, we want to develop this tire for the Corvette, let's say. So Goodyear or Michelin would come bring the tire. GM would run around all these proving grounds, evaluate it, pick a tire. So then they got where, hey, we're spending a lot of money. We're basically just developing the tire for the manufacturer. So now the push got into, hey, we want you to send us not just the tire, but we want the model with it. We want the tire model to come with it. Instead of us coming over here and paying for building a model, we want you to give us the model. And if you can't give us the model, we're not interested. So then we get the model, we spend 6 weeks running our simulation, and we turn around and say, okay, we want this tire. We're still doing their work, right? We're still evaluating their tires. So now what the movement is, and some of the idea of digital engineering is, if I can containerize and protect my simulation, and I just expose the tire model, I can give my simulation or give them access to a cloud running, my simulation's protected, and I say, hey, you work on your model until the metrics come out with handling whatever that we require. That way, they're doing the work, not us. And to do that, the system of how do I have confidence that I'm going to let my IP go is protecting that, but it's this whole modularization and ability to understand the elements that then you can allow people to compete to make the whole system better. And then that infrastructure, obviously, an environment to handle that, and then you constantly have to innovate to be able to do it faster. So really just summarizing, you know, winning at top level motorsports really is about the ability to predict and optimize faster than someone else. If I can show up faster than you and I understand the car better, you're not going to beat me. Now, there are humans in there. We see wrecks all the time. But the reason people are winning, if you watch Formula One, the reason Red Bull's dominating right now, they got a better car. They understand it. They've been able to optimize it better, and it's a constant game and battle on that. Yeah, but then execution, using that during the race is critical. But how do you bring all these tools? You know, I was always fascinated going to F1 races 20 years ago, and there's 1,600 people who used to work at Ferrari, and they spend about $1 billion a year. They made 5 vehicles. And you're like, how does 1,600 people get all this information down to be able to run the race this weekend? And it's just kind of fascinating learning how the industry has changed and how all industries are changing, trying to accomplish this. So when you watch a race, it's amazing what actually is going on behind the scenes. And there's a lot of technology and digital engineering going on. All right.
All right, we got questions. I'm pretty sure a lot of questions. Let's start with one of Eric's old classmates here.
Like a true Hassan.
Eric, can you talk about how you try to anticipate the day of race uncertainties, like, you know, weather, humidity, wind, track conditions, and all that kind of stuff, and how does that influence the different models you try to run before the races, not knowing what it's going to be like?
Well, you try to eliminate what you don't know, right? So if you think about that same thing, it used to be an after the fact. You used to say, okay, what is, you know, I measured the track temperature at this race, so I historically look back. Well, now what we're doing is trying to be more predictive. So we know the solar radiation, we know the track now, we've measured the track, so we you know, weather as good as you can predict the weather, right? But you kind of know leading into it what there's a track temperature model going on. So you're trying to get ahead of more of those things. But some of that really is where you tie in the actual telemetry and the data coming off the car. So you've predicted it's going to be a track temperature of 110 degrees, it's going to be this. Well, as you start running and the lap time is a half a second faster than what you predicted, now all of a sudden your vertical loads are a lot more. So you're trying to real time, and it happens, it's a combination, right? We're constantly working on it. There's people that sit in the command centers, most of the time they're taking laps off the car and running simulation trying to figure out what happened, like how come we missed it. But as you're able to automate that, you can then start to factor that in, and hopefully at a period of time during the race where you can make the correct decision to understand, all right, why is the car handling that way? So it's a combination of, experience of people, history, and then trying to eliminate variables. You got to know which was the most important one first, and sometimes that's hard to learn.
I am Steve Sharp, I'm the Director of Operations for the college, also a very long time short track racer. And so this is fascinating to me. I run this simulation through my head every weekend. Can't come as close to that. That's really neat. But with that being said, how are you taking the driver's individual use of the brake, the steering input, and throttle response, right, the corner exit and all that kind of thing? How are you bringing that back into the models and affecting those models? And secondary question is I'm sure you get this a lot, it's very political, and we know why people watched races back in the 80s and the 90s, and it seems like this has taken some of that out of it. How do you answer that question for the average person watching a race week to week, want to see their heroes win based on their gut instincts and things like that? How do you answer that question?
I think it's a lot of different parts of that, and I'll take the second part first because I get blamed for that a lot. Everybody's like, oh, you engineers, you killed it, right? And so the problem is it's true across all sports, right? I mean, you think about football and all the plays, the way they get called, and taking fourth downs when you wouldn't take fourth downs. All it does is raise the bar, and it keeps moving things differently. You think about those drivers, and as you came back to the first part of it, perfect example is we just got Kyle Busch over from Toyota this year at Chevrolet, right? He steps right into a car, dominates, first race wins, right? And it's so many times I've seen that a great driver can take he's arguing when he's 5th or 6th out of 40, whereas other guys you're battling to be 25th. And so over time, there's a few components of driver performance, and now I am involved with bringing youth up and kids up and short track racing and trying to work on the art of it, right? I mean, and it's, when I came into racing, it's like, all right, if I can make this race team go faster, they're going to pay me, right? I mean, no different than any value you add to another human or another company. If I can add value to your company, you're going to pay me, right? Sports is no different, right? So unfortunately, it happens. But then you start learning about, okay, now, all the cars get faster, they run closer together. If you took a car today and went and ran against someone in the 70s, you'd be 5 seconds a lap faster. It wouldn't even be close, right? So the different talent that's required when those margins are that close, you look at all the drivers getting into arguments and fights and crashes, is because it's like a fighter pilot or whatever. Your margin of how human you have to be, good you have to be, the mental processing that has to take place. Now these drivers, they're seeing all this data. They're getting out of the car, they're analyzing it. So when they're out there, they're trying to find grip in the track. They've already looked at CFD to see how their car is acting against another car. And so it still comes into their hands. It's not autonomous, at least not in this form of racing. So I think it just changes. It doesn't take it away. I think to the outside person, it looks like, okay, I could get in there and drive that car, but you can't, right? And then, and it's a different skill set, and some excel at it and some don't. That's why you kind of see, even over time, as drivers age, you're like, why did Jimmy Johnson dominate, and then why do they retire? Eventually, the heat in the car, take a NASCAR vehicle, you run 4 hours and it's about 130 degrees. I mean, there's all the floorboard and everything's about 220 degrees. Yeah, you sit in a car for 4 hours, 130 degrees, and you've lost 10 pounds. You quit. You don't think as well as you did before. And so a lot of that, we've worked on the industry to make it safer, to figure out how to make it cooler, to get carbon monoxide protection. but you're still trying to perform at that level with all these other environmental conditions. So there's still a ton of driving. But to your point, modeling, as you look at different driver modeling, particularly in offline simulation, there's these different model predictive control methods. You're looking at different modeling of drivers so there end up being these parameters. And by getting into the driver simulator, the drivers are in there, and we have telemetry now, so we can actually more quantify some of these metrics. Some drivers are really visual, like they can tell when the car is not holding the line and when you don't have enough lateral acceleration. Some drivers drive from the seat of their pants, and they're totally different. And you can put one driver in the simulator and he's throwing up, he's getting out, he's ready to literally like nauseous. And the other one, like, he don't even feel it. And so you start to understand, like, what are they keying off of, where are they looking, and then that particular response and what they do, you set your car up for those characteristics. So there's a lot of human learning going on at the same time. Oh yeah, we have a whole group that does driver performance, and they're doing eye tracking, hand-eye coordination, heat testing. Like, our 5 elite drivers in each series work with a particular group, and you may know Dan Jansen, the Olympic speed skater that's kind of famous. I know definitely the older crowd will remember who Dan Jansen is. He works with us with the drivers, so it's a lot going on there.
Eric, I guess that you probably partially answer my question. As you keep improving your AI or machine learning capability, if you will be able to fully predict, the event, would it be possible in one day you don't really need a driver?
I think, as you think about autonomous driving and you look at, our company particularly is working heavily on autonomous vehicles. We run crews in San Francisco, so there's a lot of understanding of what it takes to have the highest performance of the car, right? So there are series that do that. It's called Robo Race, and then there's some college competitions at Indianapolis. The question really is, what fun is that, right? It's still got to be entertainment. You still got to have people doing it, and so from an engineering challenge, it can be done. The question is, can you beat a driver, right? So the optimal control methods and techniques that we're doing, first time a driver gets into a simulator, we've already run what we think the optimum lap is, which is optimum driver controls and everything. And sometimes the driver can beat that because we're still not, it's like flying an unstable aircraft. Sometimes we won't quite let the stability go as far as that driver would. And then as part of the tire modeling right now is because we're not modeling the tire enough to really get the physics. Like, a lot of times it breaks away way too quick in the simulator than it does on the racetrack. So as we get better on modeling the tire, some of that kind of feeling that the driver's getting, we'll be able to pick up in engineering. We're just not there yet.
Hello, Isaac with Pack Motorsports student. When you're doing your simulation, it kind of actually goes into what he was saying.
Yeah.
Do you simulate like different tire compounds from the other companies too? So you have like the different tire compounds that get laid onto the track. So you'd have to model how much tire gets laid down for every lap, and then going in and out of grooves. Do you simulate for that kind of stuff as well?
So it depends on the series. No on NASCAR because there's one tire manufacturer. Sometimes, a Hoosier tire, a different brand, will be a practice before. We are getting much better at understanding as rubber lays into the racetrack and how it actually changes, like I said, that macro roughness and micro roughness. That particular tire, we know over laps, we can see from infrared conditions and just over an integrated amount of time what it does. That's part of the race itself. How those are elements that are really hard to be predictive because each driver could choose different lines. There's a lot of times drivers won't run in the optimum line till the last part of the race, and this one guy's up here killing them for the whole race, and then he finally moves up. So those things are hard to predict. So what happens now, all the people back at these command centers, the teams, the spotters, the second somebody takes another line, you're looking at it and trying to understand, okay, where did he make speed, right? Now, I've already known in this pit row tool, over time, I know his base car performance is better or worse than these other cars. Some of it's just he's just faster. But if you take a car that's not faster and he changes line, all of a sudden he's improved his lap time, it takes like 2 laps. And things are going off, people are talking, they're trying to tell their driver, move up, and then you start breaking the corner apart. You're saying, hey, move up entry to 3, coming low off the bottom. But if your car is having a handling issue there where his is not, sometimes you just can't do it. And so, but there's a lot of analysis of that going on.
Hey, so I was just wondering, I know that these machines are they're really purpose built, just for racing, just for doing the best times. But I wonder how much of this technology, whether it's the programming side or the hardware, how much of these processes go into production cars and helping the industry move along just for the regular person?
So again, racing used to be funded by marketing, still is funded by marketing technically. But when I came to GM, that was actually the purpose, is to move racing into engineering. So all of motorsports reports up into global product development at GM. So I sit all the time. Our tire modeling group is half production people, half racing people. So all these things that we're working on modeling are also challenges they have to be able to predict the tire models. They're running driver loop simulators to try to advance it. We are actually working on a model 27-year Corvette, the actual production car, the aerodynamics and different parts of it. So as we go forward with looking at battery technology and how quick can you charge the batteries, say in these series like Formula One that we're working on, we're tied closely with production. So all of our tools, like how we simulate a car, doing optimization, optimal control methods, we wrote papers our group did last year that some of the production cars picked up and some of the stability controls that are in some of the production cars. A lot of crossover, tremendous amount of crossover.
Regarding the introduction to F1 and under the name of Cadillac, should you hear positive news in June, I'm wondering what the schedule for introduction would be like there, and then how your team would adapt to the numerous regulation, additive eyes, budgets, and the billions and billions of dollars that go into that industry there.
So to start with, we basically had to start with our board of directors. At our Charlotte Technical Center, we had a board of directors of GM met there last October. It actually came up, there was an opportunity to talk about Formula One. So we have a budget to start with, and that's why we've aligned with a team and we're not the team, so that we can kind of take what we're learning in other series, our skill sets, and kind of be an engineering partner to the race team. So the way the process is right now, us and Andretti have an agreement to work together. So if you think about what it takes to run a Formula One team, having driver loop simulators, having full car dynos, having engine test equipment, these are all things that GM's invested in and has tremendous capability. If you're starting a race team and having to build all that, it's going to take you 30 years to build it up as well. So we provide a lot of things that are already in place, a lot of tool sets and things, and so that's our role to start with. But the timeline is if we get the entry, so we're working on the application right now, we should hear middle of June, first week of July. The plan is to race 2025 race season. So the car's already being designed and worked on. We're already doing tons of CFD work on the body surfaces, and we'll partner with an existing F1 team to buy like gearboxes and suspension and everything that we can just to be competitive to start with. But first car will be kind of done, crash testing, all the regulations you have to go through middle of next year. But 2025 is what the timeline we're on.
Good morning, I'm Brandon Mulholland with Pack Motorsports, and I like the questions about like human factors and the human element to it. So when it comes to future generations of this technology, what will prevent future crew chiefs later on from starting to get complacent, just saying that program, oh, it knows what it's saying, so I should do this. And what kind of elements can you put in place to kind of still give them that gut reaction feeling that they know this car very well than the computer may at that time?
I think, you know, again, it develops over time, right? You still have to digest all the information that's happening. A lot of times you have 20 seconds to make a decision. So, okay, yeah, as we make the tool better, and I have contended multiple times that we still can be more accurate than a crew chief today. Even 5 years ago, I claimed that. But, you know, now all of a sudden they're looking at more variables, right? You've said, okay, this tool I'm confident in can handle this. I'm going to look at other things. It's just as important, your pit crew and the humans that are down there jumping over the wall to pit the car, where's their mental state? Like, how do you give them strategy? How do you communicate? You know, coming halfway down pit road, sometimes you have to change to 2 tires. So there's still a lot of factors that you're just raising your game. You know, you're learning faster, you're digesting more information, and just making better decisions more quickly. But it still has a human can improve.
Thank you.
Yeah.
All right, so that kind of ends the question session. I think students have classes after this, I think. But I wanted to share a token of appreciation from the department and, of course, from the Zorowski family. There's a little thing that you can put on your desk. And
all right, great.
2023 Zorowski lecture plaque that you can put it. And again, let's all thank Dr. Warren again. So Dr. Warren will be here for next 15 minutes. If you want to have an informal conversation, please welcome to come by on the podium. And again, thank you, Eric, for coming, and greatly appreciate it.
Thanks, Alan.